This is part 2 of the lecture for Module 4. In this lecture, we're going to start talking about the relative frequency probability. This is sometimes called empirical or the statistical method of assigning probabilities, and is based on the observed frequency of the occurrence of events. When an experiment can be performed multiple times, the events are not equally likely. This relative frequency is the same relative frequency that we learned in Chapter 2 when we constructed the frequency distributions. Now, you may recognize this equation as a relative frequency, but in this case we're going to call it the probability of some event A is the number of times event A is observed divided by the number of times the experiment is performed. Here's an example to see how this works. So in this case, a total of 320 college students in the US were asked to state their preferred method to access the internet. And the results are here. So 123 of these students said that they prefer a smart telephone. 115 prefer a tablet. 82 prefer to use a laptop computer. So the question is, what is the probability that a student selected at random from the sample population, in this case the US, students in the US, uses a tablet to access the internet? Well, very easy. You can sum the total frequencies that we know is 320, and then we divide the number of individuals that said that they use the tablet by the total number of individuals that were interviewed. So in here I'm showing the calculation. So the probability of using a tablet is 115 from here divided by 320, the total number of participants, and that is a probability of 0.3594, or you can say, well, it's about 36%. Now the question is, well, great, I see how the probability is calculated, but is this, but you notice that this is an approximation to the exact probability because the probability is calculated from a sample. And the question is, well, how good is this probability? Or in other words, how close is this empirical or relative frequency probability to the true probability? To see that, consider this simulation. Imagine that you flip a fair coin and you record whether you observe a head or a tail, and then after each flip you calculate the relative frequency as the number of heads observed divided by the number of flips. So in the first toss, in this particular case, we obtain a head. So 1 out of 1, because there is only one, the experiment was done once, there's only one head observed, the probability is 1. If you flip the coin again, so you're repeating the experiment, and now you have another head, and now you see you have 2 out of 2, so the probability the relative frequency remains as 1. If you do the third flip, then you, in this case, tail was obtained. So now we have 2 out of 3, or a relative frequency of 0.666. If you perform the experiment again, we obtain another tail, and now we have 2 out of 4 with a relative frequency of 0.5. And then you continue this, and then you continue calculating the relative frequency as more experiments are accumulated. And then you see that the probability or the relative frequencies go from 1 all the way to 0.5. So this thing, the probability is sometimes exactly equal to the theoretical probability, sometimes it's higher, but it's jumping around quite a bit. In fact, if you were to do this, in this case I simulated it 1,000 times, you can see that the relative frequency jumps a lot, and eventually when you do it many times, the relative frequency approximates the exact probability, or what we call the theoretical probability. If we could continue this to 10,000, say, then you will see that this is very close to 0.5. And what I'm doing here is showing you what the law of large numbers says, that the more an experiment is repeated, the relative frequency probability approaches a theoretical probability. You may say, well, so what? Well, this means that if you're going to use the relative frequency approach to calculate probabilities, well, if you want a good approximation to the theoretical probability, you need large samples. That's what this is saying. So we need large samples if we're going to use the relative frequency approach to calculate a probability. So keep that in mind. All right, so the next form of assigning probability is using subjective probability. So in some cases, the outcomes of an experiment are not equally likely, and it's just impossible or very difficult to repeat the experiment. So in this case, obviously the classical approach is out of the question, and the relative frequency as well. So we cannot use it. So this is a case where experts, based on their knowledge, experience, intuition, beliefs, subjectively assign a probability that a particular event will occur. So they go like, well, I think the wind is going in that direction, so that probability is going to be so much. So that's what this is saying. So here's an example, very appropriate for what we're going through. So what is the probability that candidate A or B will win the next presidential election? Well, candidate A or B do not have an equal chance of winning the election, because every voter either will prefer this candidate or will prefer that candidate regardless of. So it's not like they say, I'm going to flip a coin and make a selection. Maybe some do, but I don't think everybody is doing it that way. The other is that we cannot repeat an election exactly. Now, by law, we cannot. The election cannot be redone. So what happens? Well, you turn on the TV or look at your favorite news outlet, and there are these political experts telling us based on polls or their experience, their knowledge, intuition, and their beliefs that such and such candidate is going to win, and by this much. So they're assigning a subjective probability to one candidate winning over another. But this is what is subjective probability. All right, so now we look at three methods of assigning probability: the theoretical probability, the relative frequency, and the subjective probability approach. As you will see, we will often rely on the relative frequency approach in practice. All right, so let's go on to the next topic, and this is the type of events. This is where I differ a little bit with the text, because I'd rather list and discuss the types of events. Once we have that knowledge, then we will apply it as different probabilities need to be calculated. All right, so we're going to use Venn diagrams. The book doesn't call them like that, but these are Venn diagrams. Typically, the square represents a sample space, and a circle or circles represent an event. And the event could be a compound or a simple event. All right, with that in mind, let's look at the first type of event, which is a complement of an event. So the complement of event A, we're going to denote it by A bar, includes all the events that are not part of A. So if this bluish circle is the event A, and the gray area is together with the elements in A is the sample space, so the complement of A is everything that is in the gray area and not in the blue area. So A complement is what is here highlighted by the gray area. To see an example, consider the experiment of rolling a 12-sided die. Here's a sample space, the outcomes from 1 to 12. And let's consider the event A consisting of rolls of 3 or less. So event A has these 3 outcomes, 1, 2, and 3. So the complement of A will be the event that does not contain 1, 2, and 3. So a complement, of course, is 4, 5, 6, 7, 8, 9, 10, 11, and 12. So I guess this illustrates the complement of an event. And we'll come back to this. This is a very important concept. All right, the other one is that the other type of an event is what we call the intersection of events. So the intersection of two events, A and B, defined on a sample space, consists of all the outcomes common to A and B, and we're going to call that event A and B. And by the way, this is covered on sections 3.42 and 4.41. Now, if two events are disjoint, or in other words, they are mutually exclusive, so there are no elements common between A and B, and we designate this as A and B equal to this 0 with a cross, which means that there are no elements in this event. So that's how it's designated. This is called an empty set. All right, but this is the intersection of events. We're looking for if there are common elements between events. Here's an example going back to the 12-sided die. And in this case, we have event A is numbers that are 6 or less. Here are the possible outcomes. All even numbers. Here are the even numbers, and all the odd numbers. So what is the intersection of A and B? Well, we need to look at A and B, and we see that the intersection contains 2, 4, and 6. So the intersection of this event will be 2, 4, and 6. And what is the intersection of B and C? Well, if we look at B and C and the elements in each of these, there are no elements in common. So that will be, that intersection will have no elements, it will be empty. All right, finally, my cursor is responding. Here are the answers. All right. The other important type of event is what we call the union of events. So the union of two events, A and B, is defined in a sample space, consists of all outcomes that belong to either A or to B or both A and B. So for example, and we designate it by A or B. So A or B in this case for not mutually exclusive events refers to every element in both events. And here we have mutually exclusive events, and A or B will be all the events in A and all the events in B. But these are the three types of events. And here is an example where we have, again, like as before, the numbers of 6 or less, all even numbers, and all odd numbers. So what is that union of A and B? Well, these are all the elements common to A and B. So in this case will be 1, 2, 3, 4, 5, 6, 8, 10, and 12. And then the intersection, the union rather, of B and C, well, is every element in B and C. There is no elements in common, but the union of these two events corresponds to the entire sample space because it contains every outcome of this experiment. And now that my cursor responded, here are the answers to these questions. All right, so we're gonna stop at this point. And so we keep in mind the three types of events that we're going to be referring to: the complement, the union, and the intersection of events. All right, in the next section, we'll talk about the probability of a complement event and other probabilities.